For today's lesson, we're going to talk about the area of a convex polygon. But before that, let us first define a matrix. What is a matrix? A matrix is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. We call it M by N matrix, meaning M determines the number of rows and N determines the number of columns. So, if we're given an example of a matrix, this particular matrix, this means that this matrix is a 2 by 2 matrix, 2 rows and 2 columns. Now, how are we going to get the determinant of this matrix? The determinant of this matrix is simply the product of A and B minus the product of C and D. So as you can see, we have the product of these two, so it's a product down minus product up. Product down minus product up. Okay, so AD minus CD. Okay, aside from that, let us differentiate a concave and a convex polygon. So concave polygons have portions of their diagonals in the exterior. So meaning that if we found a certain diagonal that is located in the exterior of a polygon, then it means that that polygon is already considered to be a concave polygon. Let us see in our example PQRS. So it's quadrilateral. The diagonal PR is inside the polygon, but the diagonal QS, as we can notice here, it's in the exterior of the polygon. So that makes the quadrilateral PQRS a concave polygon. Now, what is a convex polygon? In a convex polygon, no portion of their diagonals in the exterior. So therefore, all the diagonals of a polygon or of a specific convex polygon should be inside the polygon. So given an example, PQRS, another quadrilateral, particularly a parallelogram, this parallelogram have diagonals all inside the polygon. So therefore, that polygon is considered to be a convex polygon. So, let us try to identify some polygons, whether they are concave or convex polygon. Okay, for the first figure, what can you notice? Is it a concave polygon or a convex polygon? It's a concave polygon. Why is it a concave polygon? Some of the diagonals of this particular polygon is inside the polygon, but look at these 2 points. These 2 vertices, when we connect it together, it's also a diagonal, but that diagonal is located outside the polygon. So that makes the polygon a concave polygon. Next figure. This is a pentagon. So, is that particular pentagon a concave polygon or a convex polygon? Let's see. It's a convex polygon. So, what are the diagonals of this particular polygon? This particular point and this point, this particular point and this point, this particular point and this point. So when we connect those pairs of points, we will have some diagonals. And we could notice that all the diagonals of a polygon or of this particular polygon is inside that polygon. So that makes it a convex polygon. Next figure. Oh, that particular figure is the same as our example. So that makes us the diagonals are all located inside the polygon. So therefore, it's a convex polygon. Last figure. What is it? Is it a concave or a convex polygon? Concave it is. Why? Because there exists some diagonals that is located outside the polygon. Alright, since we know how to determine whether a polygon is a convex or a concave polygon, we can now derive the area of a convex polygon. So what are we going to focus with our convex polygons? Alright, so to derive the area of a convex polygon, we will start first in a basic polygon, which is the triangle. We want to get the area of the triangle P1, P2, and P3, okay, given its vertices. So how are we going to find the area of that? If the vertices forms a right triangle, it's easier for us to get its area. We will just get the base and the height, multiply them, and then divide it by 2 to get the area of that particular right triangle. But what if it's not? What if it's obviously not a right triangle like this? What are we going to do to be able for us to get the area of a convex polygon or that particular triangle? So as we can see in this figure, we create a line parallel to y and draw some lines from or segments from P3 up to the x-axis, P1 up to the x-axis, and P2 up to the x-axis. And the other endpoints on the x-axis would be named as M3, M1, and M2. So by doing this, we will have several trapezoids that we could form using these points. And what are those trapezoids? The first one is this particular red trapezoid, wherein we will have a vertices P3, P2, M2, and M3. What trapezoid? What other trapezoid are there? We will have this, the green one, having a vertices P3, P1, M1, and M3. And we will also have this kind of trapezoid, which is the yellow trapezoid having a vertices P1, P2, M2, and M1. So to get the area of the triangle P1, P2, and P3, we will just simply, let's go back. We will just simply get the area of this trapezoid and then subtract it to the area of the green one and subtract it to the area of the yellow one. Or get the area of the red minus the area of the two. So how are we going to do that? Okay, so let us have some vertices for each point. So we name P1 having a vertices of x of 1, y sub 1, P2 having a vertices x sub 2, y sub 2, P3 having a vertices x sub 3, y sub 3. Since we just simply drop lines parallel to this y-axis, therefore M3 is just x sub 3, 0, M1 is x sub 1, 0, and M2 is x sub 2, 0. So again, the area of the triangle is simply equal to the area of the red trapezoid minus the sum of the area of the green trapezoid and the yellow trapezoid. Okay, let's first start with the red trapezoid. What is the area of a trapezoid? The area of a trapezoid is simply 1/2 times the product of the height times the product times the sum of the two bases. So for the red one, the height would be simply the segment having endpoints M3, M2. The bases would be the segment M3, P3 and M2, P2. Now, for the height, it's this particular length. So that would be simply this. So that represents the abscissa of M2, which is x sub 2, minus this small thing here. So that would be the abscissa of M3, which is x sub 3. So that would be x sub 2 minus x sub 3. That's for the height. Now, how about for the base? M3, P3, since this one is located at the x-axis, therefore, the distance between M3 and P3 is simply y sub 3. And the distance between M2 and y sub 2, M2 and P sub 2 is simply y sub 2. So the sum of the bases would be y sub 3 plus y sub 2. And there we have the area of the red trapezoid. Now, how about for the green trapezoid? The green trapezoid having a height of M3, M1 and bases P3, M3 and P1, M1. So again, the area of the trapezoid is simply the product of the height times the sum of the bases of the trapezoid. So for the green one, our height is M3, M1. So that would be x sub 1 minus x sub 3. And then the first base, P3, M3. And then the other one would be P1, M1. So we will have y sub 1 for this base, and y sub 3 for this base. So that would be 1/2 times the quantity of x sub 1 minus x sub 3 times the quantity of y sub 3 plus y sub 1. Okay, last, we have the yellow trapezoid. The yellow trapezoid having a height of M1, M2, bases P1, M1, and P2, M2. So for the height, we will have M2 minus M1, so that's x sub 2 minus x sub 1. For the first base, we have y sub 1, and for the other base would be y sub 2. So the area would be 1/2 times the quantity of x sub 2 minus x sub 1 times the quantity of y sub 1 plus y sub 2. Okay, I will upload the next video, the continuation of this video, or the continuation of the derivation of the formula on the next video.